All right, I think we're ready. Today we're gonna keep going with beams. We're doing beam deflection today. So we've got a intro, and then we will do another lesson, I guess on tomorrow, actually on Thursday. So we've got just the intro to beam deflection. We'll probably work through a problem or two of beam deflection, but we're gonna start out with kind of the background of how we're getting to beam deflection. It's one of those sort of like centroids where there is a way that you can take the cross section for a centroid and use calculus to figure out the location of the centroid. There's that kind of same approach in the sense that we can use calculus and some theoretical type equations to develop the equations that we can use for beam deflection, but what we end up doing most of the time is using pre-built equations or pre-solved equations and use those without having to go and develop this theoretical equation every time we want to solve a beam deflection. But we're going to start with the theoretical stuff so that we know what's going on, where the numbers are coming from, how it works, what the limitations might be, and then we'll move into the more, I don't want to say cookbook, but the more pre-solved equations and how we can use those to get the same results that we would get from the theoretical approach. So, having said that, let's go over and start working on our equations. So, let's start with let's do a cantilever beam. That will work. Actually, no. Well, we'll start here, and we'll switch over to a simply supported beam soon enough. So here is a cantilever beam. Remember, they are attached at one point, so all three of your support reactions are at one point. I've always kind of drawn them as horizontal cantilevers stuck into a wall, but they don't have to be. They can be a pole that's sticking in the ground. They could be welded onto something, bolted on. So there's a lot of different ways that they could exist. This is just what we're doing for a simple approach here. We're just going to put a point load on the end of this thing, and we're going to assume that this point load is a large enough load that the cantilever would bend. And so if it were to bend, it would do something like this. You know, more or less like that. That's just my version of its deflected shape. So that's the word that we'll use, is deflection. And what we're going to develop is an equation that describes that deflection. That's our goal. So we're going to want an equation. Let me spell equation correctly. Of what we're going to call the elastic curve. Okay, that's what we're going to call it. And equation, because it's going to be some kind of y equals x, y as a function of x equals some expression. Elastic curve, because this equation that we're going to develop does have to only exist in the elastic region. So the elastic region, remember, if we go back to our, it's actually been quite a while since we did anything with this, but we have our stress and strain plot, and we had one that looked something like, something like that. This linear region over here, the one that's a straight line, that's the elastic region. And remember that somewhere up here, there is a yield strength, and if we exceed that yield strength, if the stress in the beam gets above the yield strength, then we go into the plastic region. And when we enter the plastic region, we have permanently deformed whatever it is, in this case the beam, that we would have applied the force to. And so the elastic curve is associated with the elastic region. Remember, in the elastic region, we had an equation, sigma equals E times epsilon. We called that equation Hooke's law. That was Hooke's law. And it just is where we want our parts to operate. We want our machines, our frames, our trusses, whatever we're designing, we want them to operate in the elastic region, because if they operate in the plastic region, then they've changed shape permanently. And they may not fit the way that we designed them. Now, there are cases where we intentionally send some material to the plastic region to harden it, make it tougher, stronger material, but we don't operate it there. So that's a different thing if you're thinking about, well, sometimes we do go above the yield strength. All right. So all of that's kind of background stuff, definitions. Let's get into how are we going to develop this equation of the elastic curve. So we want an actual equation. So let's go and build out a simply supported beam. So I'm going to put a roller at one end, pin at one end, and we will, do something like that. Let's just put a point load in the middle of this thing. And let's assume that if I were to push hard enough, that this cantilever beam would deflect, and it would deflect something like that. Okay. Obviously, this is way exaggerated. These beams don't deflect nearly that much. Usually it's, hundredths of an inch of deflection or something like that. So I've way exaggerated it. All right, let's do what we did. I don't remember when we did this. Oh, it was when we were developing the shear and bending diagrams. And we took a tiny little section and we looked at what the forces are. But this time, let's take that little tiny section and blow it up bigger and look at it, but as if it's deflected. It's bent. So I'm going to take that tiny section and we are going to draw it bigger. And, I'm having to draw a curve here that probably is not exactly accurate, but it's going to be close. All right, so there's our little tiny section, but blown up bigger. And it's clearly bent, it's not at all straight like it's supposed to be, and it's way over exaggerated. But let's label some stuff on here. Actually, it looks like I'm going to need to move it down because, whoa, I missed the, let me get my mouse. There we go. Maybe more like that. All right, so I probably need, it's going to be fine. I want this line to be a little more angled to match the other one. More like that, I guess. We're going to extend this line out maybe like that. That line out kind of like that. So these are just, extensions. And what they represent is an angle, right? So I could put in some angle theta. Okay? And I could remember this whole flexural stress thing. We've been saying that we've been referring to the neutral axis. The neutral axis is where the stress is 0 in our flexed beam, and the strain. Stress and strain would both be 0. Also, you could tell that from this equation, because stress equals strain times some number. So if stress is 0, then either that number, E, is 0 or the strain is 0. E is the modulus of elasticity. It is not 0 for a real material. So it's got to be that strain is 0. So I'm going to draw what I think the neutral axis is. I want to put it somewhere in the middle. It is located at the centroid of the cross-section. We didn't even talk about what cross-section this is, so it doesn't really matter. This could be a T-beam or an I-beam or a rectangular beam or a circle. Doesn't matter what the cross-section is. It has a neutral axis. So that line, we're looking at not a cross-section here. We're looking at the side view. that line represents the neutral axis running through the length of the beam. Except the section we're looking at is just a little tiny section. Little tiny section of the beam. So the distance here, I'm going to give a name. Actually, I'm going to put it over here. So I'm going to give this distance a name. I'm going to call it the radius of curvature. So I'm going to just do R, and it equals the radius of curvature. Okay. Now, you probably could not, I could not produce the equation for the radius of curvature, but there is an equation that we go look up for radius of curvature. And, well, technically for curvature, which is equal to 1 over the radius of curvature. So technically this equation is for curvature, not radius of curvature. And that equation, if we wanted to go look it up, is this. 1 over r, so curvature. I think kappa is the Greek symbol for curvature, but that we don't want that. We want this radius. So 1 over r equals second order derivative over 1 plus first order derivative squared raised to the 3/2 power. So initially, that does not look very helpful to me. It looks like, okay, there's an equation that tells me about this curvature, and I can relate it to this radius of curvature. But what do I do with that? So here's what I do with that. I recognize that something I said back here when I drew this picture in the middle, in this picture, I said that we way exaggerated this blue line, this amount of deflection. Normally, a beam that we're going to put in a frame or a building or something like that does not deflect very much at all. So this dy dx is actually, it's the slope. It's the slope at some point on the beam. So for instance, you know, that point right there, the slope of that line would be dy dx. That's actually a really small number, right? It's the slope at some point. And it is very small because I don't want the beams to deflect very much at all. If I put them in a building, they will deflect, but I don't want them deflecting very much. And I see dy dx in my equation right here. And if this is a small number and I square a small number, it gets even smaller. I add it to 1 and I raise that sum to the 3/2 power. That denominator is essentially just 1. It's 1 point some really tiny number. So with this piece of knowledge, then the denominator, 1 plus that slope squared, all of that raised to the 3/2 power, is pretty much just equal to 1. Now my equation is 1 over r equals just this. That doesn't look nearly as bad. It's still a second order derivative, but it's not nearly as bad as what I had before. So that looks useful. Okay. Let's carry on with our diagram here. I'm going to draw another line. So I'll make this one red, and I'll just put it, well, that was not, that's better. All right, so this line, this is just a different line. It doesn't matter that I drew it below it or any particular thing. It's just a different line, not the neutral axis. And I have made it some distance y. So going back to our my over I, our flexural stress equation, the one we've been doing, this would just represent y. It's some distance away from the neutral axis. Normally, we make that distance all the way to the top or bottom of the beam. that's fine. I just picked some random distance. All right. Now what I want to do is I want to combine this idea of the radius of curvature being r and the idea that I've got the neutral axis with no stress and strain on it, and I've got this other axis, red one, the red axis, and it's some other distance. So if I were to do the length of the neutral axis. Now here, the neutral axis, and remember I'm only dealing with one little segment, one little arc theta here of the beam, but I could extend that to the whole beam with these calculus methods. The length of the neutral axis is an arc length. So that would equal, the way I've got it labeled here, r times theta, right? That's how you calculate an arc length. If I did the length of the red line, it would equal, well, r is the radius of curvature to the neutral axis, but I've added in this distance y, so it would equal r plus y times theta. No matter what y is, y might be a negative number, so it's actually shorter, and y might be a longer number, like the way I've drawn it here, and the arc length is longer. But that would be how I would calculate the arc length of any line that I drew on this little diagram that I've worked up. Okay. Then remember, this is going back to maybe the first week, but remember that strain, so remember that was our symbol for strain. Strain is defined to be we had axial strain and we had a shear strain. This would be an axial strain. Even though things are flexed and bent, the lines I've drawn are still like either the axis or parallel to the axis of this beam, the longitudinal axis. So strain, axial strain that we're talking about, I'll go ahead and write axial. Axial strain is defined to be change in length divided by original length. My pages are all blowing around over here off the screen. Okay, so the change in length, if I think about the neutral axis, remember we call it the neutral axis because it is the place along the beam that has no strain, no stress, no strain. But this red axis that I've drawn, and any other axis that I would draw, would have stress and strain on it. And so if I did change in length from how much the red axis, how much strain is on this red axis, I would do change in length. Well, that would be the length of the red line minus the length of the neutral axis. And then the original length would be the original length of the neutral axis. Okay, so here, if I expanded my r plus y, just kind of unsimplify my equation, I've got r times theta plus y times theta minus r times theta over r times theta. And I've got a bunch of r times thetas in there, and I've got a bunch of thetas in there. Well, actually not everything has an r theta, but I do have a r theta minus r theta, so let's do different colors. R theta minus r theta, those go away. And then theta, theta, and this equation simplifies down to calculating the axial strain on any axis, I just happen to pick the red one here, equals y over that radius of curvature. Okay. I could also remember that, let's go back to Hooke's law. I am trying to develop the equation of the elastic curve. So I want to stay in the elastic region where Hooke's law defines the region. So sigma equals E times epsilon. Let's write that down. Sigma equals E times epsilon. Okay. I already have previously, not today, but previously the past couple of weeks, developed an equation for sigma for beams that are flexing. And I said that sigma equals negative m times y over I. Now, I put that negative sign in there as part of our sign convention to get tension on the bottom of the beam to be a positive value and all that kind of stuff. Let's ignore that right now and just drop the negative sign off just to make things a little bit clearer in our equation. So I'm going to plug in that for sigma equals E, and I'm going to plug in this for epsilon. And now I've got an interesting equation. This one has y on both sides, so we can get rid of that guy. And then my equation is m over I. Let's move that e over there also. So m over I times e equals 1 over r. And I've got this guy that gives me a value for 1 over r. So it says it's the second order derivative of y with respect to x. So now m over, and normally for whatever reason I do ei. Obviously you can put them in any order, they're just multiplied together, equals 1 over r, which is my second order derivative here. Normally you're going to write this equation the other way around. And normally m, the bending moment, is not constant. Remember, it changes throughout the length of the beam. It's a function of x. So that's what I'm going to work with. So this equation is useful to us. It is not the equation of the elastic curve. In fact, it's not a deflection equation at all. But it gives us a way to relate the curvature, or the radius of curvature is what I'm interested in, but the curvature related to the bending moment in the beam, a material property, so what material is it made out of, that's E, and then I is what shape is the beam, the moment of inertia for the cross section of the beam. So it relates all the things that would change the amount of deflection into this second order derivative thing. So let's see how we would use that to actually calculate beam deflection. So that equation's important. We'll do that so we know it's important. Let's go back to our little cantilever beam, the one we started with. It doesn't matter. It doesn't matter that we took a simply supported beam to draw this diagram, because the reason I did this is so that our curvature was tension on the bottom, but in a cantilever beam is most likely tension on the top of the beam, but you could develop the exact same thing. It would be upside down. So doesn't matter. It still applies. So let's use I'm probably on the wrong color. Cantilever beam. I'm still on the wrong color. Cantilever beam, and let's say that let's just make this beam a rectangle. So there's this little cross section. It's just a rectangle, like a 2x4 or something like that. I don't know. Okay, let's make this one generic so it doesn't have numbers in it. It's going to have letter variables. So there will be our force. I'm going to just call it a point load P. And our distance, our length here, I'm just going to call L. I am going to do one kind of strange thing. And I'm going to say that our x-axis starts here and goes this way. And I'm gonna do that for a particular reason for our sign conventions later on. But it's fine if we made x start at the wall and like we normally would. But this is just going to help us with one of our equations later on. And normally we would not count from that direction, but it's fine. So what that does is what we need to do, if we're going to solve this equation I've got in the yellow box, I need an equation for m of x. I need to solve m of x. We've done that before. It's been a while, but we cut the beam open at some point, and we drew our cut open beam. You know, I'm going to show that we've cut it open there. We put our point load on the end. This distance that I cut, I don't know it, but it is x. This is also a reason why I have x starting at the end of the beam, the free end, and counting the other direction. There is an internal shear force. I'm not interested in the shear force. I am interested in this moment. That's what I want to solve. So I would do summation of moments about this cut surface. I'll just say clockwise moments are positive, and I will do, well, it looks like P times X equals M of X. So there's my equation. This is about as simple of an equation as I can use. Obviously, you could have way more complicated equations. You might even have multiple sections in the beam where each section has its own equation if there are more loads and distributed loads and all this kind of stuff. We've done some like that, but it's been a week and a half or so when we did that kind of process. But the point is, we could get an equation for the internal bending moment. Here, I've just chosen a very simple equation so that we can see the process. We're not normally going to do this process. This is just the background of what we are going to do. All right. So actually, I think I did, that should be a negative though, right? Because I skipped a step in there writing my equation. So actually, M of X is negative P times X. All right, let's go to plugging this into our equation. So we've got this equation. And we've currently got a value for M of X. So let's plug this in and start doing a little bit of calculus, not too much, just a little. So we've got this equals M of X is now negative P times X over E times I. E and I are just constants. I don't really need to know what they are right now, but for E, I would find out the material. You know, this is a particular material, steel. I would go find its modulus of elasticity in a chart somewhere. I is a moment of inertia that is related to the cross section. I said that this cross section was a rectangle, so the moment of inertia would be BH cubed over 12. The point right now is not to actually solve for the deflection, it's to develop the equation of the elastic curve. So I'm just going to leave it as constants E and I. All right, so what I need to start doing is in order to get rid of these differentials here, I need to start integrating. So I'm going to integrate the left side with respect to X. I'm using X because X is the longitudinal axis of the beam. So I want to basically be able to move from X equals 0 all the way to X equals L and figure out what the deflection is at any one of those points. Okay, I'll also integrate the right-hand side. So the integral of negative p times x over ei with respect to x. So the left-hand side is really simple. If I integrate the second order derivative, I get the first order derivative. So dy dx. Which, by the way, remember, slope of deflection. So this equation that I'm about to generate, that will give me the slope at any point. So I drew one. Where to draw it? You know, that one little line right in there. That's the slope at that point. But I could use any point x and I could calculate the slope at that point. So that could be useful. Integrating the right-hand side, I would get E and I are both constant. P is constant, it's the constant force. So the only variable is actually x. So I would just take the negative. We had a little disconnect there. Hopefully we're back. It looks like, there we go. So you might have missed a little bit. I was just integrating the right-hand side. P, E, and I are all constants. The negative sign is constant. So I integrated the integral of x dx, which is just x squared. And it also generated a C1 constant of integration. In fact, I'll note that. So we do need to find a value for what the constant of integration is. So in order to do that, I need some boundary condition. So if we go back to our original picture here, I know that at x equals L, so here, that point is x equals L. And I know that this current equation is talking about dy dx, which is, by the way, I could just replace that with the slope at x. So the slope is a function of x. I'm going to go ahead and move that ei over here just to get it out of the way. And then I've got negative p x squared over 2. Oh, yeah, I left out the 2, didn't I? I should have had a 2 right here. The integral of x dx is x squared over 2. So I forgot that 2. Plus C1. So at x equals L. So again, remember I did a weird thing where x equals 0 at the free end and x equals L at the wall. I know that at the wall, theta of L equals 0. No slope at the wall. The beam attached, assuming I built the beam horizontal, then the part of it that's at the wall stays horizontal, and then it starts deflecting based on what load I put on it. If I plug these in, then I will get the left-hand side of the equation is no slope, so theta equals 0, equals, I've got x equals L, so negative p L squared over 2 plus C1. So therefore, C1, I just move it to the other side. Actually, I'll move the negative PL squared to the other side. And C1 will equal PL squared over 2. Taking that value and plugging it into my equation that I previously had, I would end up with theta. Actually, well, this is fine. Theta of x times EI equals negative p x squared over 2 plus PL squared over 2. I am going to go back one step, kind of undo one thing I just did. But this is the equation for the slope at any point on our beam, on our point load on the end of a cantilever beam. This would give us the slope at any point on that beam. I am going to go back a step and say dy dx instead of theta, just to make the next step a little clearer, times e times I equals negative p x squared over 2 plus p l squared over 2. Now we've got the first order derivative on the left hand side. So what are we going to do? Integrate dy dx with respect to x. I'm going to put that ei out in front because it's just all of this stuff. Negative p x squared over 2 plus p l squared over 2 with respect to x. Okay? Now, when I integrate the left hand side, I get e times I. The integral of dy dx with respect to x is just y. Y, in this case, y is a function of x. That is what I want to solve. I want to solve for y of x, or y as a function of x. And this right-hand side, pl squared over 2, that's all constant, so those are just going to get multiplied by an x. I do have the x squared, so that's going to become x cubed over 3. So when I integrate this, I'll get negative p x cubed over 3, but times 2, so that's 6, plus all of this, p l squared over 2 is just multiplied by x. And then I get another constant of integration, c2. Okay, so I need to solve for c2. And again, at x equals L, the wall, y equals 0. There's no deflection at the wall. So there's no slope and no deflection at the wall. Okay, so if I plug this guy in again, the left-hand side becomes 0 because it's multiplied by y of x, which was 0, equals, I've plugged in L, so negative p l cubed over 6 plus p l squared times x, which is L, so that's L cubed over 2 plus c2. And I can figure out that c2 equals, if I solve these, I get negative pl cubed over 3. Okay? And then, if I plug it all together, I get e times I times y of x equals negative p x cubed over 6 plus p l squared times x over 2 minus p l cubed, that should be a cubed, over 3. And it'd probably be better if I wrote this way, where I take the EI and maybe do something like that. And I have a equation. This is the equation of the elastic curve but this only applies for a cantilever beam with a point load at the free end. Whoops, V. So what you can imagine from there is, one, you could either develop whatever, it doesn't, not just cantilevers, but any kind of beam, as long as you could find an equation for m of x in every little section of the beam where m of x might be a different equation. And you could go through and, plug it into our second order curvature equation here and work your way through integrating to get the slope at any point, and then integrating that to get the deflection at any point. And you could develop any equation for whatever kind of beam you might have with whatever loading you might have. Fortunately, we don't have to do that very often. We have tables. Let's see. We have tables that I think I put one here. Here's a link to a chart with common beam deflection. So let's see if that's still active. Oh, here's a chart. So we have tables like this, where now you'll notice here, there's a cantilever beam with a point load on the end of it. They have a different form of the equation than what we ended up with, but they also started with x equals 0 at the wall, and so ours is backwards from that. So they have a different equation, but it models the same curve, just from a different perspective. But there are, charts like this with all sorts of equations for pre-done for you, so you don't have to go through the calculus. Here's a similar one. It's a cantilever beam, but the point load's not at the end. So you've got a different equation here, two different equations, one for one section and one for another section. So you can see where here's one with a distributed load that tapers off to nothing. So there's all kinds of different equations you can find, and that's what we're going to use. The thing about these is, even with this set, I have 10 here. I think your exam reference has 8. Even with these, you could still easily imagine a scenario that these don't cover. Maybe you've got a point load on a cantilever beam, but you also have a distributed load on that beam. Now I've got both of those cases, case 1 here, case 1 and case 3 are those things, but they're not combined together. So what we'll be able to do is employ the idea of superposition. So superposition is where you take one, in this case, load. You might have heard of superposition in circuits, maybe. But you take one load, calculate its effect, take another load, calculate its effect, add those two effects together, and you have superimposed those effects on top of one another, and the result is the effect of the two loads together. So some things you can do that. Some things they're independent, and you can use superposition to add their effects together. And so that's what we'll end up doing to create more and more complex scenarios out of a relatively simple set of equations. Why don't we, since we haven't done anything other than very, very generalized stuff, let's get an example and see if we can work through it with actual numbers. Let's see if I can find one in WebWork that we can do. Let's see. I forgot to look ahead of time, but let's see. Let's see if there's one in the optional 2 somewhere. There may not be, actually. Beam design. Yeah, there's not in optional 2. Let's see. Where else might there be one? Where are the others? Oh, here we go. Let's see. 17. What has it got? Beam deflection. All right. So this one. This one's relatively simple. It would give us the idea of what we're doing, but it's pretty simple. Maybe this one. This one looks like it's got some stuff going on. So this one, and it says it's 3 out of 5 difficulty rating, so maybe not too hard for us. All right. So let's see what we've got. We've got, all right, so this is a named beam. There's its beam designation. Let's see if we can get that a little larger for you. We've got some dimensions on it. We've got 1 point load, and that's it. But it's not really a cantilever. It's kind of a simply supported beam with a cantilevered section. So we've got to figure out what that does. We're going to neglect self-weight. So sometimes that's not true. So sometimes you can't neglect the self-weight. unless a beam, not a beam, unless a problem that we're going to give you, unless it says to consider the self-weight, then the assumption is you're going to neglect the self-weight. If you need to deal with the weight of the beam, then what you'll do is you will go in and basically put a distributed load. Remember, this value right here is the weight of the beam. In this case, I think it's actually the mass, so I think it's kilograms per meter, maybe. We'd have to look in the chart to see what that represents. But unless it specifically says to consider it, the assumption is we're going to neglect the weight of the beam. All right, we want to find the slope at B, deflection midway between the supports, and the deflection at C. Okay, so first of all, let's redraw our little beam picture. So I have a pin, then a roller, and then a point load. Pin there, roller not at the end, somewhere in here, and a point load that is at the end of the beam. So this pin, even though I kind of looked like I didn't connect it to the, there we go. This pin is holding the left end down. I think that was point A, holding point A down. And so what I imagine this beam looking like if it were to bend a lot, I would imagine it does something like this. Right? So between the pin and the roller, it's actually bent upwards. And then the part that's overhanging, the cantilever section, is bending downwards like you would expect a cantilever to bend. So that's kind of usually what you want to do first, is try to imagine what is this thing going to bend like. They want us to find the slope at B. So A, B, C, let's go ahead and put those in. This is A, B, and C. Let's put our dimensions on there. Let's see, A to B is 6.5 meters. And B to C, got a lot going on down in there, is 3.3 meters. This is a W406. So W, wide flanged I-beam, 406 is how many millimeters deep it is. So it's actually a pretty big, massive beam. Weighs 100 kilograms per meter. We'll need that value to get the moment of inertia for this thing. All right, so the slope at B. What I think I would do here is, first of all, the slope at B is probably going to be determined by, it's, let's see, let's do green. That is what I want to calculate, that slope. I kind of missed the line there, but you get the idea. I want that angle theta. I think how I can do this is I need to create the effect of the point load, but I need to be able to use one of these equations. Whoops. So I want to use this here. Case 9. I want to use a concentrated moment and calculate the slope where that moment is. So I'm going to take this. This is not quite superposition. This is, or at least this piece isn't. I'm going to say that, well, this, at least at B, this is equivalent to this beam. So there. It's equivalent to that beam. with a concentrated moment. The value of that concentrated moment would be, actually I don't know my force, 43 kilonewtons. So 43 kilonewtons times 3.3 meters equals 43 times 3.3, 141.9 kilonewton meters. Okay, so you do have to be a little bit creative and kind of understand how a point load at some distance, well, it does create a moment. A load at a distance creates a moment. And does that create the same effect as what I have here? If, for instance, this 142 kilonewton meter moment at B does not create the same effect out here at C. So at point C, I couldn't say that I'm going to use this 142 kilonewton meter moment at B and calculate something over at C, because that's not the same. So there is a little bit of visualization of how the beam is actually bending, and that's why I drew the blue line first, is kind of to get a visual of what I think the beam is doing when it's bending. And I think that a point load at the distance BC is the same, at least at B, as a moment, where I translate that point load over to B as a concentrated moment. Same effect on the bending of the beam. This I have a case for. So let's go see what it is. Let me copy. We wanted slope, so we need these equations. Make them bigger. All right, so I actually have two different values for theta. I have theta 1 over on the left-hand side, theta 2 on the right-hand side. It's not important that it's left and right. Theta 1 and theta 2 are in relation to where is the concentrated moment. So unfortunately, in this case, my beam is exactly like this one, the one that I've drawn up here, other than I have a clockwise moment, and that one on my picture is showing counterclockwise. So I'll actually get a negative of whatever is shown here because my moment's different. But I would go in this distance here. The problem says is 6.5 meters. And I would take the theta 2 equation, so this equation, and plug in all the values. So M, I have the opposite of this arrow, so I have negative, so this will be theta at B. I have a negative 141.9. Those are kilonewton meters though, so I have to be careful with my units. I might have to multiply by 1,000. Times L. Now this L here does not refer to my beam. It refers to, the diagram next to it. So in this case, L is the distance between the two supports. That's 6.5 meters. Over 3 times E. So E is a material property. We need to go to our problem statement. It says that this is structural steel. Structural steel, and we're in metric units. So we need to go and find the modulus of elasticity in metric units for structural steel. Let's open a new one because we need to go back to that diagram. This will be here. And material property, whoops, I missed it. Material properties. We want the metric ones, not the US ones. There are, like structural steel, E is 29 million. If you took that number and converted it over, you would not get the same number that's going to be in this chart. So you need to look at the actual chart. And it says 200 gigapascals. Okay. So E is 200, but that's gigapascals, so that's times 10 to the 9th pascals. And then I, we're going to have to get from a chart. Let's go, this is a W beam, so let's go and look for the W beams. W sections. Oh, I don't know if I have... Those are the US units. All right, so we're going to have to actually look in our exam reference and find the W chart in metric units. There's W. There's S. I don't see W here. These must be all of the... oh, wait. No, that's WT, C, C, WT. Maybe it's in exam reference 1 and I just didn't see. Oh, I didn't want to download that. Oh, by the way, these are the, this is the reference you have. So there's only 8 here. The difference is the one that I'm looking at online or in Canvas has unevenly distributed loads in it, and this set does not. There's the W. All right, so let's zoom in on this guy. Oh, can I not? Wow. All right, so I need W4 something. 406. Maybe we can get this out of here. I may have to download it to see it. I don't know. It's going to be that column. All right, let's see what we have. Very blurry, but we have W406 by 100, and that one lines up with this set of numbers. I think that says 397. I'm not sure, but I think that's what it's trying to tell me. We might be off a little bit. Those units are, let me make sure I know the units for that. Those units are 10 to the 6th millimeters to the 4th. I think that's 10 to the 6th. Yeah. All right. Okay. So this would be 397 times 10 to the 6th millimeters to the 4th. So this might be the hardest part of these problems, is particularly in the metric setup. There are some mix-max units, so you've got to make sure that when you plug everything in, you've got a cohesive set of units here. So I'm going to rearrange this into newtons and meters. So theta B equals negative 141,900 Newton meters times 6.5 meters. 3 times 200 times 10 to the 9th pascals. Pascal is Newton per meter squared, so it's fine. Times 397 times 10 to the 6th, but those are millimeters to the 4th, so I need to multiply that by this conversion factor. Okay, so let's see. This is really a better setup for MathCAD or something, but on an exam, you've got a calculator. All right, 397. Convert that guy over. Multiply by 200 gigapascals, so that's 10 to the 9th. Times 3. There's my denominator, hopefully. 141,900 times 6.5 divided by my denominator. So I get a super tiny number, which I expect. I get I get 3.872 times 10 to the negative third. And the units here, this is a slope, but there's nothing in here about degrees or anything. So this is actually radians. So if I want degrees out of that, I need to multiply by 180 and divide by pi. And I get 0.222 degrees. Now, does WebWork agree with me? I don't know. Let's find out. WebWork wants, it wanted the radian number, which is what we had, 00387, 00387. So we were correct on that case. All right, let's see. Let's do a little bit more. So the problem then asks us for the deflection midway between the supports. Well, that one's not too big of a change. Actually, I don't think we'll do that one, but look here. Where's our reference? We would just use this guy right here, this equation off to the right. We do have the deflection equation for the whole curve. Actually, no, I have, this is the curve equation right here in the middle. And then I have the maximum deflection, and I have the deflection at the center. So in that case, I would just plug in this value to get deflection at the center of the supports. So that's pretty straightforward. No sense in doing that one. But it also asks for the deflection of the beam at point C. That one's a little trickier to figure out. So why don't we try to figure that one out? So the thing with it, let's look here. The thing with it is that the point load, 43 kilonewtons, is acting like a point load at the end of the cantilever for just this section BC. So the point load is kind of acting like cantilever for that section right there, the pink one. The problem is that the cantilever doesn't start out horizontal. It starts out at some angle here, theta. Fortunately, we just calculated that angle right here. So I'm going to treat this section, this pink section, like a cantilever, but I'm going to tilt it by the angle, the 0.22 degrees. So if I were to draw it, I would do something. This is what I would imagine I'm solving. I would draw, let's see, can I even do this? I'm not sure. Yes. So there's the cantilever with the point load on it. And then I would imagine that it's already tilted some amount. And that amount is the 22 degrees. Or no, 0.22 degrees, sorry. And then the point load causes the cantilever to bend some more. So that's how I'm going to deal with the amount of deflection here, is I'm going to basically add on the deflection because it's already tilted a little bit from the angle at B. So let's see if we can make this work. So what I end up wanting to calculate is I want to calculate this distance here. That's the answer I'm looking for. And it's made up of two parts. That part is delta from the theta equals 0.22 degrees. And this is, I guess I should have done it that way. This is delta from P equals whatever it was, 43 point, no, what was it? 43 kilonewtons. So this one's sort of superposition-y, but it's also not exactly superposition-ish, but it's related to superposition. All right. So let's do the delta from the 0.22. So that one, what I'm going to do is I'm going to kind of employ the same idea that these are actually small angles. 0.22 degrees is not a big angle. And I'm going to say that the delta here, delta from theta, let's move it up. That's fine here. Delta from theta is equal to the length of BC. Why am I writing? I don't want to write this as an equation. All right. Delta from theta equals the length of BC times theta. So it's an arc length. So technically, you know, that's a little arc instead of just going straight down. But since it's such a small angle, they're essentially the same number. So BC, the length of BC is 3.3 meters. Theta is theta in radians. Let's not use degrees here. Theta in radians is 3.872 times 10 to the negative third. So that delta is 0.003872 times 3.3, 0.0128. Those would be meters. So that would be this distance. So not a non-zero number, but a really small number. All right, 1 millimeter. Now we need to add to it the deflection from the cantilever beam with the point load on the end of it. So let's go back to our chart and find that over here. Cantilever beam with a point load on the end of it. This is the equation I need right here. I do need to make sure E is going to be the same. It's the same beam, same material. I is going to be the same. It's the same beam, same cross section. P, the point load, is the 43 kilonewtons. L, I need to be careful with L here. So L is, let's go to look at our chart. L is the length from the point load to where the cantilever beam ends. That's what it's showing me in my beam type column here. So I need that value. Here, that value is from the point load to where the cantilever section ends. It doesn't end at a wall in this case, but it's where the cantilevered section ends, is only 3.3 meters. So I need to make sure L in this equation is 3.3 meters. And L in the previous one was 6 point whatever meters. So delta from the point load equals P 43, and that's 1,000 newtons, times L 3.3 meters, but it's cubed, over, and I think that's the exact same denominator, 3EI. Yeah, that one was 3EI also. So if I had saved that denominator, I'd already have it, but I didn't. So 200 gigapascals for E. And I, the value was 397 times 10 to the 6th millimeters to the 4th. And then I went ahead and converted that over to meters. Just to keep track of it. All right, so let's see if I can do all that again correctly. 397, and then we got to convert it to meters to the 4th, multiply it times 200 gigapascals, and times 3, and then the numerator is 43,000 times L cubed, And then we got to divide by our answer, denominator. All right, so I get a really small number. Let's see. This is actual deflection in meters. So the previous one was angle, slope in radians. I get 6.487 times 10 to the negative third meters, which would give me my total delta at C equal to what I call the delta from theta plus the delta from the point load. So I've got 0.0128 meters plus, they're both going down. So technically, you might want negative numbers because they're deflecting downwards. Our problem didn't actually give us an X and Y axis. Oh, here, look. Denote upwards deflections with positive values and downward deflections with negative values. So it does want a negative. And then this would be 0.006. Oh, no, that's only... no, yeah, it would be 2 zeros. 487 meters, right? Let's check our answer. Oh, I got 019. Yeah, 019 meters. And negative. So downward deflections are negative though. Okay, so we will do more of these. Oh wait, how did you find the delta from theta? So that's an arc length. It's not an equation. This equation here, so this one, what I'm doing is, I don't really know how to draw it in here very well, but I'm basically saying that I'm pivoting back here at the roller. Now I've drawn it on the top here, but and the end of the beam is making a little arc length here. And to calculate arc length, you do r times theta. In this case, the radius is the length of that section BC. So, and that's what I did here. That's the radius that I'm sweeping through, and theta is the angle I'm sweeping through. But the angle needs to be in radians, not degrees. So this is just an arc length equation. With radians, with theta equal to radians, not degrees. I can't say that, will you have to do this exact same process somewhere? Maybe, maybe not. Well, this is a homework problem, so you'll have to do it on the homework problem, and you'll have different numbers. It's probably pretty finicky because these are all super tiny numbers. You've got 10 to the negative thirds and things like that, so you probably need to carry a bunch of decimals to make web work happy. But this is not the most common thing. Next time, Thursday, tomorrow, we'll do a couple of more superpositions. We'll do one like really basic, just add two things together, and then we'll do another one where maybe it's a little more similar to this one, but different problem. All right, so I think that's a good stopping point for today. We're going to do more. This is kind of there are beam deflection problems on exam 2. This is the last topic that's on exam 2. So exam 2 is frames. We started with frames. Technically machines are also in there. up to this beam deflection stuff. So it's all related to flexural stress, beam deflection, frames that have beams in them. It's all related to the same stuff. And we'll take that exam, I think, next week, maybe. I have to look on Canvas to see when I've got it scheduled, but it's a week from now, more or less. But this is the last topic that's on there, is beam deflection. We're not doing, you're not having to do this version of beam deflection. We're only doing this version of beam deflection. So it'll be pretty straightforward on the exam, because I don't like the reason most people miss these problems are just in the the little details. There's lots of, like, you got to keep your units straight and that sort of stuff. And when you're in a time test and working by hand, that can get a little tricky. And you're probably doing the idea of the problem right, but you made a little error on plugging something in the calculator. I'm surprised I didn't. And so there's not a big focus on beam deflection on exam 2, but there is some. One problem probably, maybe two if I feel like it, but probably just one problem, and it'll be, one of these style things. All right, we'll be back tomorrow at noon, and we'll do some more beam deflection. Probably good time to start if you have questions from the preceding web work that you want to go through. We should have time to talk through that also. I don't remember if I have a day. Let's look. I don't remember if I have a day set up that's exam 2 review or not. Let's see. Yeah, so actually that'll be Monday's class, with the exam being the Friday of that, or the Thursday of that week. So if you have some questions on this coming Thursday, then we can ask those, but I also have Monday as basically just question and answer day. All right, we'll be back tomorrow. A little bit more beam deflection, not a long topic left for that. Most of just question answering, and then Monday is just question answering. Quiz 3 I think is open, so you should be able to do that one. Quiz 4 is about to open, so you can do that one next week if you want to. So we're over the hump for this class. So from here on out, the topics are less massive, I would say. They're a lot more streamlined type of content after exam 2. All right, I will see y'all tomorrow.